Fantastic. Thank you all for showing up. I say this like every day, but I really do mean it. Like, thank you for showing up and being ready to learn and to investigate some of the mathematical phenomena that we find in our world. Now, we do definitely find this in the world. So let's take a look at some of the concrete examples where you're going to see exponents live and working. So let's say you have a tennis tournament and it's single elimination. You lose, you're out of the tournament. Every round, one player plays another player, and after that round, only one will remain. So every round of this tournament, half of the players remain that were there before. If we start such a tournament with 256 players, and every day each player plays a match and gets eliminated, how many matches would there be in this tournament if you were one of these players? How many matches would you need to win in a row if you were to win this tournament? You'd say 8? How do you know this? Great. So here, let's take a look at how we could look at this in a table. And that's kind of how did you do it that way? Like you kind of divided, and found the answer? Great. So that's definitely one way to do it. So we can analyze these things in graphs, tables, and equations. And we're going to get good at using all three tools to analyze exponential situations. Let's take a look at what this situation looks like in terms of a table, because that's going to be the most intuitive for us to understand. Here is number of matches that have been played, and we're going to compare that to number of players left. In this case, does it make sense to look at negative number of matches played? Not at all. So we won't have that. But does it make sense to look at the situation where 0 matches have been played? Yeah, that's as we start the tournament, before anyone's eliminated. So let's start our table there. Notice that we made some decisions about our domain for this function, and we decided 0 was a good place to start, and then we'll increase. Does it make sense to consider when half a match has been played? Also, no. So we're going to have integers for matches. We're going to have 1 match has been played, 2 matches has been played, and 3 matches, 4 matches. And Emily has indicated that if we go to 8 matches, we'll be done. Let's take a look. So at 0 matches played, we'll have all the players still there, 256. After 1 match has been played, how many players will there be? And your calculator will tell you that's true. An easy way to do that in your head, to divide this by 2, is to say, well, 250, I can divide 250 in my head pretty easy. That's 125. And then I also have to divide 6 in my head. That's 3. And then just do 125 plus 3. Right? And then we do another division to get to the second match, and that would be 64. The third match, 32. 16 players left. 5 players left. We have 8. 6 matches played. We have 4 players left, so we're the final 4. 7 matches played, and we have determined the 2 people that will square off for the championship. The championship match is the 8th match, and after that match has been played, we'll have our champion. So Emily is correct. You will need to win 8 matches in a row in order for that to be correct. Yep. So each one of these matches is reducing the number of players in this tournament by half. And we see that they started with the right number of players so that we ended up with a single champion. If you were running an event like this and you had 300 entrants, you'd need to find a way to trim your bottom 44 entrants to maybe take them out of the tournament. Maybe you have a round robin at the beginning and the worst 44 players don't enter this kind of elimination tournament. You'll notice things like the Stanley Cup playoffs or the World Cup or what have you always organize their tournament with some power of 2 number of contestants. The Stanley Cup will be played by 16 hockey teams every year, and they don't let a 17th team in because that'd be craziness. Major League Baseball in the same way. They'll have wild card games and different sort of play-in type tournaments to determine who gets to be the 8 teams that play for the World Series. Let's keep going. So now we've got our table of values. We can even graph this situation. So let's go ahead and graph it. You're going to be able to see your table of values at the same time as your graph, but I don't because I did that in the wrong spot. Anyway, after 0 matches have been, but I happen to remember the values, so who cares? After 0 matches have been played, it's like at the beginning of our tournament, we had 256 players, so we're there. After 1, and you'll notice 1 is between 0 and 2, it's right there. After 1 match has been played, we have 128. So if I count here, that's 110, 120, 130. So 128 is just below 130. That's about right there. You can label some of these points too. That's 1 match has been played, 128 players remaining. And then keep going. 2 matches have been played. We have 64. So 64 is about right there. So go ahead and graph your table of values. 3 matches played, that's 32. 4 matches have been played, that's 16. 5 matches played, that's 8 left. And so you could label any of these points that you want. Here's the point 4, 16, 5, 8, 6, 4, 7, 2, and 8, 1. Okay. Notice that gets really, really close to 0, but it's never quite 0. And we wouldn't play a 9th match because the champion doesn't need to play against themselves to determine which half of them is the best tennis player. That'd be weird. Maybe you could. You put up a wall and play against a wall. No, doesn't make any sense. So we would stop our tournament there at 8-1. And now we can join. Well, you can join. I probably can't because I'm really clumsy with this technology for graphing beautiful curves. But you can join these points with a beautiful curve here. Notice that in the beginning, it's descending very quickly, but then it slows its rate of descent. And it slows its rate of descent, and it slows its rate of descent, and it slows its rate of descent. Oops, and then I start missing points like crazy. And that's kind of not terrible, but it's kind of not bad. And this is the shape of exponential curves that we're going to see. This is an example of what we would call exponential decay, where the value of the function is getting lower as x increases. We see it's increasing very quickly it's decreasing very quickly in the beginning. The number of players getting knocked out early in the tournament is very large. And then the rate at which players is being knocked out slows down until it almost stops there. So you see that there's a real curvy type of shape to this type of graph. Right. Now, the last thing that we would want to take a look at, basically with our table, we can investigate all the questions that I asked. So Emily identified we needed to divide 8 times to finish this tournament. So that's the number of matches the champion will win. If we wanted to know how many matches do we need to play to get to the Sweet 16, like if you're looking at the 64 tournaments in college basketball in March Madness every year, right? So they start again with a power of 2, and then they'll go from 64 to 32 to the Sweet 16 to the, what's the round of 8 called? And then the Final 4, and then the championship match. So anyway, in this case, how many matches do we need to play to get to 16 players remaining? Well, we need to actually only play 4 matches to get to 16 there. And then there will be, after the 4th match, so like the 5th match will be played by 16 players, and we would have. But what would an equation look like? We haven't needed an equation in this situation yet, but I'll show you what one would look like. In this situation, we would have an amount of players, and it would be a function of the number of matches played. So we'll use x equals number of matches, and a is the amount of players left. Okay. In this case, it's equal to, we started with 256, and then we cut that number in half every time we played a match. So in these cases, you're going to see your variable show up as your exponent up there. Now let's take a quick look at that in Desmos, see what it looks like, and see if it matches the graph that we created. Oh, those are other Desmos situations. So here, this one is pretty good. So if we look at 256 multiplied by 0.5 raised to the power x. So there is our tournament. And it looks just like our equation, what we had there. Notice the same shape. Notice that after we have played 5 matches, we have 8 players left. After 7 matches, we have 2 players left. And after 8 matches, we're down to 1 player and only 1 player. Now, in this situation, the numbers in between numbers don't make any sense because we can't have fractions of a player and we can't play fractions of a match. You either play the match or you don't. You count as a player or you don't. So this should actually be a set of integers, a set of integer points. Now, for the next situation, let's take a look. And we'll probably need our equation a little bit more for this situation. In this situation, we have the happy situation of bunnies that triple their population every year. If in January 2022 of this year there were 18 bunnies, we can actually use that to create not only a table, we can also build an equation for this. Right? So let's take a look at how we break down and build an equation for this type of thing, and then we can investigate a few different things like, in the future, how many bunnies will there be at specific times? So our first step in something like this is we can let x equal the number of years since 2022. And that's important information that we know when we're starting our stopwatch, like when time 0 is. So here, when x is 0, time is 2022. If I put in x is 1, I'm talking about 2023. So that's an important let statement. It helps you really organize your thinking about what the different values of x mean. And then here are some things that I want to identify. I know that I start with 18 bunnies. So 18 is the initial value. That's important information. And this here, this tells me how they grow. So this is going to give me the number 3, because if I want to triple something in math, if I want to triple a number like a triple 10, I either add itself to itself 3 times, or I multiply by 3. Just multiply by 3. So 3, we call this number the growth factor. Okay. In our previous example, our growth factor was 1/2. We were multiplying by 0.5 every time we went through another match, or dividing by 2. Dividing by 2 is the same thing as multiplying by 0.5, so it doesn't really matter which one you do. Down here, we know these bunnies triple their population every year, so our growth factor is 3. Now, can we use these things, 3 being the growth factor and 18 being the initial value, to create an equation? Well, I'll walk you through it for this one. First, we can say that the population of bunnies is a function of time going on. And because we've said let x be our time, then we would have a function would be read like this. Population is a function of time. And it's equal to, well, I know I want to start with 18 bunnies, and I'm going to be multiplying that by 3 every time a year goes by. So let's take a look. We'll start with a table here and investigate what our table does. If x is 0 years have gone by, then we know that wants to be 18. But I'm multiplying 18 times 3? Not at all. Like, I never multiplied by 3. Just 18. It's just what it is. But after 1 year, how many bunnies will there be? It'll be 18 multiplied by 3. It should triple. Okay. And then after 2 years, what's going to happen to the population? Well, that population growth after 1 year, all of those new bunnies, they triple their numbers as well. So we'll have 18 times 3, but then times 3 again. And then notice what's happening to the bunnies in this graph. Every time I go forward 1 year, I multiplied their population by 3. And we have a really convenient tool for doing that. It's exponents. instead of like doing, if I want to know how many bunnies will there be in 10 years, instead of doing times 3 times 3 times 3 10 times, I can do 3 to the 10. So I'm starting to see a pattern here. What if I wanted to know how many bunnies there were in 2021, 1 year ago in the past? There's 18 bunnies this year. How many bunnies were there last year if their numbers are tripling?
Is it a negative exponent?
You can use a negative exponent here. Yeah. Anyone tell me how many bunnies last year? 6 bunnies. Now, how did you do that? Yeah, you're going to divide by the growth factor going back in time. You're going to multiply by the growth factor going forward in time. In this situation, if we knew that there was like a pre-match, maybe a match before the tournament started with a larger field, and it was also single elimination. I don't know why we're calling it a different event, but there must have been multiply by 2 number of players in that. Or divide by 0.5 is the same thing as multiply by 2. So we're going back in time to a higher point on that curve. Here, we use division. So this would be 18 divided by 3 here, or just 6. Okay, so that gives us some ideas of what we need to be doing with this equation. If I have this equation here and I raise 3 to the power time, this is the correct equation. If I start at year 0, notice what happens. Year 0, I would have 18 multiplied by 3 to the 0. Remind me, if I raise something to the power 0, what do I get? 1. Anything to the power 0 is 1. So I just get the initial value back. It's 18 times 1. So that works. If I go forward 1 year in time, I will be multiplying by 3 once. I triple once. So that makes sense. If I go forward 2 years in time, I have 3 to the 2. I'm multiplying by 3 twice. And this will continue mapping the growth of these bunnies as I go forward in time. So let's go ahead and put what we have on our graph in the table so far. So we said at 0, we had 28 bunnies. How are we going to graph? 18 bunnies. How are we going to graph 18 here? This is already 100. Holy. Well, 18 would be way down there. So that's the point 18. And 1 year ago, we only had 6. It's very, very tiny. And then 2 years ago, my goodness, how many bunnies were there 2 years ago? Sorry?
6 times 3 to 2.
Yeah, that's where your Adam and Eve bunnies were. Your Adam and Eve bunnies were 2 years ago. So 2 years ago, we had 2 bunnies. And because these points are really hard to see on the graph, we could just label them like -2, and there were 2 bunnies. Here, 1 year ago, so it's -1, there were 6 bunnies. And then we have here 0 years, 18 bunnies. That's 2002. Okay. And then going forward 1 year in time, let's get our calculator out and we'll put it together some values. 18 multiplied by 3 gives us the number of bunnies in year 1. So that's 54. Why am I showing you such big values up to like 15,000, I wonder? Let's see. Well, let's do here 18 bunnies multiplied by 3 to the 2. That will tell me how many bunnies in the second year. 162. So go ahead and put that on. There's 162 about there. It's starting to grow. All right, let's see how many bunnies in the third year. So to do the third year, I'm going to still have 18. And I multiply that by 3, raised to the power, and I use my x to the y button here, raised to the power 3, equals, 486 bunnies. Oh, that's a lot of bunnies. Almost 500. 486, so we'll call it there. Maybe I label this point 3, 486. Cool. And now let's do the fourth year. 18 multiplied by 3 raised to the power 4. 1,500 bunnies. Very nearly 1,500 bunnies. Wow. So we're up to about there now. So this population of bunnies, at this scale, you can hardly see it growing at all until the bunnies start overwhelming everything. Wherever you look, it's all bunnies. And you see, they just start growing so fast here, these bunnies. My goodness. And their population is just going to explode there if we let them continue tripling. Probably will introduce wolves to the environment or something to control their population. Otherwise, we'll have a bunny apocalypse. So there's our graph of what it looks like. And in this case, we can use this to see like how many bunnies will there be in January 2026. Would you use your graph, your table, or your equation to solve this type of problem? You could use your equation. All are good tools to use. If I was building the table, I would probably be using an equation to build the table anyway. So, how would we use our equation to solve this question? How many bunnies in January 2026? If 2022 is year zero, what year is that?
That'd be year 4, so 18 to 3, 18 times 3 to the 4.
Good. So to solve this question, you take your p to the x is equal to 18 times 3 to the x equation and say, well, I'm going to evaluate the population in year 4. And that's going to be equal to 18 multiplied by 3 to the 4. We usually put this 3 in brackets. It's the growth factor. And we're going to raise that to the power 4. Okay. We've already done that. Is this point here? And it's on my calculator still. It's 1,458. So the population in that year is going to be 1,458. Now, in this situation, does it make sense to consider how many bunnies will there be in half a year? Or in like some number of months? Could I use this function to calculate how many bunnies there'll be after, let's say, in July 2023? How many years have gone by if it's July 2023? 1.5?
Close to that.
That's what I was going for. Is a year and 6 months, so 1.5 years. Well, let's try it. We can go onto our calculator here, and we can go p of 1.5 because July 2023 is going to be a year and a half. Bunnies are going to be reproducing fairly continuously over the year, and so it's not going to be like the tennis tournament example where it doesn't make sense to consider what happens after 1.5 matches. You either played one match or two matches, but not in between. In this case, you can have fractional numbers or decimal numbers of years. And we'll see, we can use exponents in this case, and your calculator will handle them just fine. So this is going to be equal to 18 multiplied by 3 raised to the power 1.5. So let's see how we punch that in our calculators. I'm going to do 18 multiplied by 3, and then I use this x to the y button, and I raise it to the power 1.5, and say equals. Well, there's going to be, 93.5. Will there be such a thing as 93 and a half bunnies? It's too terrible to consider. So rather than considering that, round to the nearest whole number of bunnies. Okay, so we will have 94 bunnies at that time after a year and a half. Okay. So the value of p at 1.5 is equal to about, and I might put approximately equal by rounding. We said 95 bunnies. There you go, 95 bunnies. Let's see what happened on our graph. Here is 1.5 years here. And it looks like my graph, I was a little bit high. That suggests that it's like a little bit over 100 from my graph. If I zoom in, you'll see I bubbled kind of upwards with that. It should rather be joining my curve like that. This would be the correct answer there, about 94. But we can see with that continuous line between my points, I get a pretty good estimate using a graphical method for solving these types of problems. So graph, tables, and equations, we can generate them all with exponential decay and exponential growth. Let's take a look at one more example where Carmen is investing money in a new startup, and she's very lucky. This new startup averages 12% return on investment for 35 years. So let's see how much money her $1,000 investment is worth at different times going forward. So, first of all, How much money, if she invests $1,000, how much money will there be there after 1 year? If it grows by 12%. How would we do that? How would we grow this number 1,000 by 12%? Do you happen to know what 12% of 1,000 is?
I don't know what the number is, but I do know how to get what your 12% would be.
Okay.
So if it starts off at 1,000, which the average will return 12% over the 35 years,
Yep.
it will be you times it by 0.12 of the total, and it will give you what the 12% is.
Right. So, okay, so here Noah has a good idea that this 12%, I can express that as a decimal. Some of you will be using the percent button on your calculator, and I want to kind of encourage you not to do that. Converting to a decimal shows me you understand what that number 12% is. 100% is 1 as a decimal. Like if I'm 100% of 42 years old, that's true. I multiply 42 by 1, I get 42. That's how old I am. In this case, if you were growing something by 12%, there's two ways you can do it. So Noah's way is we have $1,000 and we multiply by 0.12, and then we're going to get $120, and that's 12% of 1,000. That's how much it increases by. That's the amount of increase. So to find the total amount of money that our investment will be worth after that 1 year, you have to add back on $1,000. So to find the total, then we would add 1,000 plus 120 to get 1,120 bucks. Right? That's how much it's worth. But there's another way that you can do in one step. And this is the way that we're going to take a look at, because it's going to translate to this idea of exponential growth much more directly. But we want to have Noah's way of understanding this as to why I can do this. When I add 1,000 to 120, what I'm doing is adding 100% of the number to 12% of the number to get 112% of the number. You see, if it grows by 12% after 1 year, there will be 112% of that thing. So instead of multiplying by 0.12 and then adding back on the initial 100, what we can do is just multiply 1,000 by 1.12. This is 112% as a decimal. We can see that we're multiplying by a number bigger than 1. When we multiply by numbers bigger than 1, things grow. And when we multiply by numbers between 0 and 1, they get smaller. So in this case, it's going to grow. So we're happy with that. That also gives us the same answer of $1,120. Okay. So, first of all, I meant to do this one first. Before we evaluate it, just do your gut feeling. How much will this investment be worth after 35 years? 2,000, 5,000, 8,000, 20,000? What are you thinking? Was that 24, did you say? But 24,000? We have a guess, 24,000. Anyone higher or lower? What do you think? All right. Let's do 100% participation here with a show of hands. Everyone's hand up. Everyone put your hands up. And take your hand down when I get to a number that you think, no, it can't possibly be that much. Okay? This will be worth $5,000 after 35 years. $10,000.
I can't answer because I need on my calculator.
$20,000. $30,000. Some hands are starting to go down. $40,000. $50,000. Okay, almost all the hands are down. $60,000. Okay, all the hands are down by 60. So it was between 30 and 60,000 that people are expecting. Actually, your intuition here is really good. Either that or you looked at the graph paper. 30K to 60K. Okay, so this is what we're expecting. This is our guesses. Always start with a guess in these types of situations because it works your guessing muscles. It's going to make you a better guesser of these types of things, and that's a valuable skill. So be good at estimation. Second reason is when your calculator spits out a number, you want to have something to compare that to say, did I make a calculator error or not? So the guess is very useful for a lot of reasons. Let's keep going. Can we create an equation for this situation? Absolutely we can. What is our initial value of money? It's $1,000. Great. And what's our growth factor? In other words, how much does this grow by? What do I multiply by to find out what it does after 1 year? Yeah, 1.12. Yeah, growth factor is 1.12. Every year it will be 12% more than it was last year. So 12% more than 100%. And so now we can build an equation. The amount of money that our investment will be worth will be a function of time. We could use X or we can use T here. Both are okay. It's a letter. You can choose whatever letter you want. The amount of money is a function of time, and it's equal to $1,000 multiplied by 1.12 raised to the power time. This is our function. So now let's see if we can find out in which year her investment will grow to more than $10,000. Right? We can absolutely create a graph for this situation. So let's go ahead and do that. And in order to do that, well, I can put on here's 10,000, 5,000, so $1,000. Here's her investment down about there. That's where it starts. Pretty humble based on the scale of this graph, right? Pretty cool. Okay, now let's build a table of values. And in this table of values, I'm kind of giving you a hint here that we want to look up to about 35. So let's take a look at these values. For different values of time and the amount of money that she will have. I would not recommend looking at 0, 1, 2, 3, 4, 5. You don't need that much detail. We're going to be fine looking at 5 years, 10 years, 20 years, 30 years, and then let's look at 35 years. Okay? We're going to use this function. A is a function of time is equal to $1,000 multiplied by 1.12 raised to the power time to generate these values. So let's go ahead. Punch them on your calculator. And so get your calculator out, start working it, see if you can work faster than I can. 1,000 multiplied by 1.12. But then I'm going to multiply by that growth 5 times to find out how much money there's going to be there after 5 years. So we get a decent amount of growth in the first 5 years. It almost doubles, about 1,750 or so. I'm going to round to the nearest 10 because there's no way I can show this kind of detail. Oh, 1,760, sorry. No way I can show more detail than to the nearest 10 on my graph. So I'm happy to round. Okay, let's go $1,000 multiplied by 1.12 raised to the power 10. Oh, now it's more than tripled in 10 years. Very cool. Our money is tripling in 10 years. That's awesome. So 31.1. 3,100 and about $10. I'm rounding. Now let's see it in 20 years. If it tripled in 10 years, what's your prediction for 20 years? Should it be 6,000? More like 9,000. Good, good. Yeah, because 3 squared is 9, not 6. Good. So 1,000 multiplied by, again, we're growing by 1.12. We'll raise that to the power 10 to find out how much it is in 10 years. And yet, I already did that. Darn. 1,000 times 1.12 raised to the power 20. There we have, it's about 965. 9,650 or so. Great. Let's do 30. This is going to triple again, right? It'll be about 27,000. And then, so here, 1,000, multiplied by 1.12, raised to the power 30 we want. That's almost 30,000. I'm going to round to 30,000 here. That's just so close. After 30 years, it's 30 times in value. It's about 30,000. And then let's find out after 35 years. $1,000 multiplied by 1.12 raised to the power 35 gives us about $53,000. Plot your points. Plot of these points. So we have 5 years, about $2,000. Looks like nothing much has happened at this scale, but believe me, something has happened. It's almost doubled. After 10 years, it's almost tripled. Wait, that's 5,000 there. Yeah, so it's still good. And then after 20 years, we skipped 15, no problem. After 20 years, it's about up at 10. It's almost 10. So it's about there. Really gentle so far, right? Hardly much anything is happening. After 30 years, though, we're up at 30,000 up there. And after 35 years, we're at 53. So there's 50. 53 would be about there. And so we see the same type of shape that we saw with the bunnies. We see the same type of shape that we saw with the tennis match, that it's growing. And it doesn't look like much growth is happening until, whoa, wait a minute, something real is happening there. There's some real growth happening with that money. And that increasing trend is going to continue increasing as we continue increasing values of x. So to summarize our learning here, we can create equations of this type for situations of growth and decay, and they look like this. The amount of something is a function of time, and it's equal to the initial amount multiplied by the growth factor raised to the power time. And A, this is the initial amount, and B is our growth factor. And T is your unit of time. In the case of the money and the bunnies, the unit of time that we were looking at was a year. But you could easily have something like a viral video that increases the number of views it has by 50% each day, and be using T as some number of days. It depends on your situation, what T is going to be measured in. Now, how do we build these Bs, these growth factor Bs? If I tell you something is doubling, then your growth factor would be 2. If I tell you something is tripling, then your growth factor would be 3. But it gets tricky when I say something grows by 30% or something like that. So B, what you can do is say B is equal to 100% or 1 plus R. And now what's this number R? Where R is the percent growth as a decimal. So if you knew that you were growing by 12%, R as a decimal would be 0.12. That's the number Noah used to find $120. And then we add that to 100%, or we add it to 1 to create our growth factor of 1.012. Now, many of you will make this mistake of trying this problem here and using 0.12 as your growth factor, and you'll say, why is it shrinking instead of growing? Because you forgot to add 1. It's probably the most common place where I see students making an error. Let's take a look in Desmos at what that error looks like. So here in Desmos, I think I have it in here somewhere. Here is her money. This is the curve that we built. So here is 35, and it grew to about 53,000. So that matches our curve. But if I, instead of having 1.12 there, I had 0, notice what happens to this curve. It shrinks so darn fast. After 1 year, only 1 year, she only has 12% of her money left. She only has $120. After 2 years, she has 12% of that, or $14 left. And it's going to get smaller, 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 because it's not the right growth factor. That's not growing by 12%. That's shrinking by 88% a year. That's 100% minus 88%, or you're left with 12%. So that's why adding this 1, it makes a critical difference to these types of problems, where now you see growth. Doesn't look like much in the beginning, but look at that curve explode over time. After 50 years with that company, she has over $300,000, and that came from only $1,000 investment. So that's a pretty cool return on investment. Of course, 50 years is a long time, and 12% interest is very, very, very good. Very good. Now, what I encourage you to try, working on your own, try to conquer this example. If you invest $100 at 9% interest and you want to know when you'll have $500, use a graph to find the answer. I think your method here is going to be create an equation, use your equation to populate a table of values, graph your table of values, and then find approximately where you're going to have 500 bucks. There's algebraic ways of doing it, but you'll learn them in grade 12. Okay, and any questions, hit me up by email. Thank you for showing up for your learning, everyone.